a massive city on a deadly floodplain. London's Thames Barrier holds the line against powerful storm tides. It's the most powerful and durable locomotive working today. The diesel-electric is a workhorse and power plant all in one. Ever wonder what's going on under your feet when you're pumping gas? Inside the self-serve gas pump. Win, place, or show. When it's nose-to-nose and stakes are high, all bets are on the photo finish camera. Let's take the lid off these machines and see how they work. This is the Thames Water Barrier, the single most important flood defense system in the world. There are other barriers, but none come close to this machine's burden of protecting over 1 million people and billions in real estate. Its job is simple: stop a river from putting London underwater. Let's see how it works. Stretch a set of gates 520 meters across the River Thames to block it. Now, do it in just minutes as thousands of tons of water rush towards you. Then, when the threat's over, retract the gates quickly to let boat traffic through. And keep it working for decades without ever breaking down. The barrier was first used in 1983 to halt a storm surge from the North Sea. Surges that slam into the mouth of the Thames are a huge threat to London. Combine a storm with the river's high tides, and you've got a major disaster. Big parts of London would be swamped by floodwaters. So, to protect people and the city, engineers had to figure out how to block the Thames while maintaining its shipping channels. Their first big challenge was location. They chose a spot 15 kilometers from the Houses of Parliament, where the banks are straight and the riverbed sturdy enough for a massive concrete foundation. There are 10 gates in total that span the Thames. 6 sector gates that rise from the river. These include 4 large central gates and 2 outer ones. There are 4 smaller gates by the riverbanks that live above the water unless they're in use. All of the gates are hollow and made of steel. They fill with water when submerged and empty when rising from the river. Each of the 4 large gates is a hefty 3,300 tons, almost half the weight of the Eiffel Tower. The next challenge was how to get the gates out of the way quickly and safely. These radial arms drive the sector gates under the water to lie flat in concrete sills on the riverbed. This allows the free passage of river traffic. If forecasters spot a threatening storm, they notify the Port of London so that shipping in the area can be given the heads up. Red X's on the barrier tell ships to stay put. Operators in this tower control the movement of the gates. The closing sequence is designed to work with the natural flow of the river. After the outer gates are dropped, the sector gates are raised in pairs from the outside in. If the command center's computers were to crash mid-emergency, each pier has its own set of independent controls. And if they fail, the rams can be manually cranked. With millions of people and billions in property behind this barrier, nothing's left to chance. Even these radial arms are doubled up. Each one is powerful enough to move a gate on its own if the other arm breaks. They're powered by sets of hydraulic pistons. The top arm pulls in, while the bottom one pushes out. This rotates the sector gates up and into a defensive position. Operators normally close the barrier in about 90 minutes. In an extreme emergency, the entire thing can be set in place in just 15. But if you shut it all at once, the force of the entire river hits the barrier at the same time. And that could send a deadly rebound wave back downriver. If floodwaters ever threaten to top the gates, they're raised a little more to allow a controlled amount of water through. This is called an underspill position. It kind of acts like a dam controlling the levels of a reservoir. The closest any flood has come to topping the barrier is 2 meters. So far, so good. The entire operation is electric and has 3 independent sources of power. Electricity from the grid flows through cables in tunnels beneath the river. If the tunnels flood or power gets cut, there are 3 backup generators, each powerful enough to operate the entire barrier. The electrical bill for 1 turn of these screws? Almost 6,000 euros. On to the final challenge. The gates need constant maintenance to fight rust and water damage. How do you get that done without shutting down? By designing the whole thing for high and dry repairs. The gates come with an extra hydraulic piston to rotate them up and out of the water, so workers can repair damage and touch up the paint job. The gates do spend most of their time underwater, so paint is needed to fight rust. It takes about 40 tons of paint, figure 10,000 cans, just to cover 1 of the 4 large gates. The barrier has averaged about 5 closures per year since it opened. But if forecasters are right, there could be as many as 30 per year in the coming decades. And that's quite simply because water levels have been rising steadily. Only time will tell how long this astounding work of engineering will hold up. It's among the most powerful, most durable train engines working today. The diesel-electric locomotive is a workhorse and power plant all in one. It can haul thousands of tons of cars at speeds of up to 200 kilometers an hour. And it can work on almost any type of track because it produces its own power. The word locomotive means self-propelled vehicle. And its challenges have always been the same. Create enough power to move cargo and people, haul them quickly and efficiently over distance, then stop them smoothly and safely. Let's see how it works. Straight electric locomotives need power from the grid to move. To keep them in business, you need expensive and hard-to-maintain overhead wires or electrified rails. But not all rail lines are connected to the grid. And if you're rolling on them, you need a diesel-electric locomotive, like this one. Producing power is straightforward on this machine. A diesel engine spins a generator that produces electricity. The electricity flows to traction motors on each of the axles. And they spin the wheels. You'd think it would be easier to get the engine to directly spin the wheels, like in a car. But then you'd need a massive transmission to handle different torques, speeds, and loads. The transmission would have so many gears, you'd need another train car just to carry them. Electric motors don't need transmissions. Increase the flow of electricity, and you increase their speed and power. Simple as that. A 16-valve diesel engine that puts out about 3,000 horsepower spins a generator that produces over 2 megawatts of electricity, enough to keep 500 homes lit up year-round. That's a lot of juice, and it all goes to the traction motors located on each axle. This locomotive weighs in at 80 tons and has enough power to move over 30 times that amount. That's a lot of weight riding on the rails. So these machines rely on steel wheels to stay online. Other materials, like rubber, would warp and burn a lot of the locomotive's energy just to overcome friction. But this material has some problems of its own. Steel on steel is very slippery. And when shaped like this, all that weight can balance on the surface area of a dime. This helps with efficiency, but it sure causes problems with traction. Going around corners isn't an issue because the wheels have flanges to keep them on the track. But what about accelerating? To get started, engineers blow sand onto the tracks to give the machine all the grip it needs. The real work for this machine is managing all that weight when it's moving. To stop an object in motion, you have to convert all its kinetic energy into something else, like heat. A speeding bullet has way too much energy for glass to stop it. But thick steel is able to convert the bullet's energy into enough heat to melt it. Try stopping a locomotive pulling a full load of cars traveling at 200 kilometers an hour. Its kinetic energy is equivalent to 1,000 kilograms of TNT. Which is why fully loaded trains need about 2 kilometers to stop. When it's time to slow down, power to the motors is cut off. The wheels are now spinning the electric motors. This bleeds energy from the wheels, and they slow down. It's called dynamic braking. Most of the kinetic energy from the wheels is converted into heat that's dissipated through onboard resistors. Air-powered disc brakes also help out. Their spring-loaded pads are held open by air pressure. When you activate the brakes, the air pressure escapes and the pads close on the disc. And there's always sand available if they need more traction. What happens if the engineer falls asleep? This thing's basically a bomb on wheels. Which is why most locomotives come with a dead man switch. Unless the guy driving this thing hits this button every 30 seconds, an alarm sounds, and the machine automatically shuts down. The locomotive has been a giant in the transportation business for almost 2 centuries. Pound for pound, it's still the most efficient way to move goods and people over land. And thanks to the latest innovations, it shows no signs of giving up its crown. Gas stations pump out billions of liters of gas every day around the world. At one time, gas station employees had to do the pumping for us. And it's thanks to this vending machine that we now get to do it by ourselves. The self-serve fuel dispenser is like a robotic bartender. It measures, mixes, pours, calculates, and then gives us the bill. And because we're the ones handling a hazardous cocktail, this machine also makes sure we do it safely. Here's how it works. When we squeeze the handle and pour, 3 questions. How is the accounting done? What makes it stop when our tank is full? And if there's a spark, what prevents the tank and us from going up in flames? Gas pumps can deliver the goods in multiple grades, but they usually offer 3: regular, mid-grade, and high octane. The fuel comes from subterranean tanks that can hold up to 50,000 liters each. Most stations have 2. One stores regular, the other high octane. So where do the other grades come from? Simple. The system just mixes fuel from the two tanks and delivers exactly what you order. No matter what button you push, this little device gets it to your car. A submersible pump draws in the liquid gas and sends it out through a hose that connects to the nozzle. As soon as that happens, the counting begins. Along its path, the fuel fills a flow meter, a metal chamber that contains a rotor. It's called a pulsar, and it measures 1 liter of gas every 4 turns. An onboard calculator multiplies that number by the gas price and displays your running total. But there are problems with measuring gasoline and getting your money's worth when the temperature outside rises or falls. The density of gas shifts 1% for every 10 degrees of outside temperature change. If it heats up, gas expands. Cools down, it contracts. So if the temperature goes up during the day, you're going to get less gas on the drive home. Fortunately, these probes keep track of changes in temperature and regulate the flow of gas according to where the mercury is at. Meanwhile, we're squeezing the nozzle for all it's worth to get this over with. How does the pump know when to shut itself off? The gas pump comes with an auto cutoff system. It's a small tube that runs from the outside tip of the nozzle up to a sensor inside the handle. As your tank fills up, the nozzle becomes submerged. This chokes off the air pressure that was holding the handle open and shuts down the flow of gas with a familiar click. This is what protects us from getting splashed with liquid fuel. But how does it protect us from the explosive gasoline vapors that are released during pumping? A small motor is used to create a vacuum that sucks excess vapor from the nozzle. But the machine can't capture all the vapor, and that means there's always potential for danger. When sliding in and out of your car, you can create static electricity. If that hits the vapor, watch out. It's no urban myth. It happens. Luckily, gas vapor needs oxygen to burn. That means the flames could never reach the oxygen-free fuel tanks. Not enough O2? No explosion. Same goes for inside your tank. And when you get back in the car and turn the keys, you'll see this. That's because a styrofoam float has made it to the top of the tank, pushing up a metal rod that sends an electric signal to the fuel gauge, signaling that it's full. So the next time you're filling up, relax. There's a lot going on under your feet and in the box beside you to make sure the only bad thing about the experience is how much it costs. This is a digital photo finish camera, found at the end of every major race. It's a machine that can help make you a fortune or break your heart and bank account. Whether it's pointed at men, machines, or animals, there's no arguing with its results. Even if these photos look nothing like an average snapshot. Let's see how it works. Photo finish cameras do 3 things that normal cameras can't. Fit the end of an entire race into one frame, capture the exact moment each one crosses the line, and get a clear shot of all the competitors, even if one blocks another from view. But the photo finish camera doesn't just hang around waiting for the finish. An internal stopwatch is triggered inside the camera at the beginning of every race. And measuring them isn't just about the finish line. For results to count, competitors have to start on an even foot. At a horse race, the photo finish camera needs a starting gate. After the horses are loaded in, spring-loaded gates are shut and locked in place by these arms that are connected to a magnetic roll bar. When the starter hits the button, the magnet turns off, the bars release, and the gates fire open. And this machine stands by, ready to fire. It's an ultra-precise, ultra-sharp camera that costs about 8,000 euros. But you wouldn't want to use it for your vacation pics. It takes images that are just a few pixels wide, the perfect width to capture the finish. Just before the horses hit the line, the operator presses a button and the camera starts firing at up to 3,000 frames per second. Each line image gets fed to a central computer, which arranges them side by side. Add it all up, you get this, the ultimate collage. That contains as many as 50,000 photographs. So while a normal snapshot shows one moment in time, a photo finish actually shows one location spread over many moments in time. Its high perch gives the camera an excellent angle on the proceedings. But there's always a chance of this: two bodies floating in the same digital space and time. So the camera uses a trackside mirror to produce a reverse angle. This captures all the horses, no matter where they are. Nothing escapes its digital eye. Once the last horse crosses the line, the operator edits out gaps so all the competitors fit on one screen. This image may be all gamblers and fans care about, but this machine knows a world record could also be on the line. As the photos come in, each one is tagged with a time, more accurate than 1,000th of a second. Line up the cursor with any competitor, and it tells you the exact moment they cross the line. This is what announcers mean when they say they're waiting for an official time. Totally unbiased, never blinks an eye, and it always tells the truth, one line at a time.